Thanks everybody for making time on a Friday afternoon. Super happy to be here. Like Mark said, I'm faculty in electrical and computer engineering at UWCE. So to start with the ideas, the motivation for my work is the observation that the way we interact with the physical world is increasingly mediated by machines. And this can take the form of teleoperated robots, where we're at a haptic console, stereo vision, et cetera, to do robot-assisted surgeries that can improve surgical outcomes. It could be an invasive brain-machine neural implanted interface to control a robot. You know, if I'm paralyzed from the neck down like Jan, and I want to be able to feed myself again and have that autonomy and that kind of sense of identity and self, these machines can restore that for me. And it could be in augmenting or amplifying human ability. So the final example, Steve Collins, one of your folks here, created this, in this case, a purely passive device that reduced the metabolic cost of walking, which is a really extraordinary accomplishment. But then they have active devices that even decrease it even further. And I think is just hinting at the possibilities that we have for either mitigating disability or just amplifying innate abilities in people. And so the goal of my research, the kind of fundamental questions that drive me, are how to predict the outcomes when humans and machines interact in these ways, and then how to shape those outcomes toward, you know, better devices that work, perform better, or that are more usable or preferable for the users. So that kind of sets up the structure for today's talk. I'm going to talk about kind of a constellation of results that build toward trying to predict and shape outcomes of these interactions. We're going to take it step by step and kind of piece by piece, not kind of tackle it all at once, but have kind of a sequence of results that culminate in that. And so there are sort of two parts of the talk. First part is about a third of it, and then the second part is about 2/3 of it. So first we're going to talk about the kinds of models that people learn when they're controlling machines. And then subsequently we're going to leverage our knowledge about those models to synthesize how machines should learn from and interact with people. So the way that we try to study the kinds of models people build when they're controlling machines is a paradigm. We use a paradigm that goes back decades. So like the folks interested in fighter pilots in the 50s were already developing some of the kinds of techniques and paradigms that we use. So we have the human, we have the robot, the remote robot that they're controlling through some interface. And just to acclimate us to the notation and the kind of terminology and stuff, there's going to be some input that the human provides to the machine. So it's the human's output, but it's the input to the machine. And then there's going to be some output from the machine that's displayed back to the human. And in some of the experiments I'll talk about, that human input is manual. It's like a joystick. In another set of experiments, it's going to be myoelectric, muscle activity based. And then I'm only going to be talking about visual displays. There could be other display modalities like haptics, but I'm not going to talk about that today. And then in addition, there's going to be these extra signals that we think about. There's going to be a reference R that the users are tasked with tracking. So they're trying to make their output, or not their output, they're trying to make the machine's output track some specified reference signal. And then there's going to be some disturbances that are coming in and kind of jostling things around and making the task harder. And also, as it turns out, revealing some information about the human transformations that we can only get by applying that disturbance. And so the way that I like to think about these systems, I'm a control theorist by training, and so everything to me is a block diagram and a dynamical system model and the interconnection between those things. And so here, this is just kind of a schematic representation of the picture, the cartoon that I had in the previous slide. But we're going to be able to kind of cash out this picture into math and into learning methods that we can apply to the system. And the kind of first fundamental question I have is, what's in the box, right? What exactly is happening inside this human transformation? The human is looking at the reference they want to track. They're looking at the error with respect to that reference. And then they're producing their control signal U that's feeding into the machine. And there are a lot of hypotheses about what's inside the box. Ideas going back decades are that there are forward models and inverse models. So the human's learning, if they're controlling their own body, they're learning the kinematics and dynamics of their arm, for instance. And then an inverse model that lets the human compute, if I want my arm or the cursor on the screen to do something, go through some squiggle on the screen, then what is the input I should supply to get it to do that? And this is the terminology that's common in the motor control literature. To be kind of more consistent with the controls literature, again, the school of thought I come from, we're going to talk about feed-forward controllers. And feed-forward controllers are supposed to approximate the inverse of forward models, or machine dynamics that are being controlled. And another reason we like thinking about things this way is that this came from the motor control world, but there are really strong parallels in the fields that engineers roll in, control theory, AI, machine learning, et cetera. So now if I return to this picture, and I want to understand what's inside that box, we have a hypothesis that there are two principal mechanisms.
Please enter the meeting passcode, followed by the pound sign.
Solely on the reference that the human's trying to track, and then a feedback mechanism that operates solely on the error that they're currently observing between where they are and where they want to be.
You are in the meeting now.
Like I said, these diagrams aren't just pretty pictures. We can actually use them, cache them out computationally. So we can take the block diagram, we can transcribe it into a system of equations that's kind of an equivalent representation. The block diagram just happens to be a graphical representation of some algebraic identities, but we can actually cache those out. And then we can manipulate these in order to estimate quantities of interest. So what's important about the equations in step 2 are that the transformations of interest, F and B, the feed-forward and feedback transformations, we can't directly measure those. Those are inside the box. Like I don't get to go in and carve into the human's brain. Maybe some people, some neuroscientists can come up with methods to do that. I don't think that way. But what we can do is measure the input-output behavior for the human transformations, HUR and HUD, the way that they respond to these exogenous signals we're plugging into the system. And then through these algebraic manipulations, we can get estimates, unbiased estimates of the transformations of interest. So we apply this in an experimental paradigm where somebody's sitting at a computer and they're seeing a reference squiggle on the screen, and then they're controlling the cursor, the purple cursor, through for instance, a manual interface to try to track it. And the kind of results we get for the feed-forward and feedback controllers look like this. What I'm showing are the Bode plots, which if you come from a controls or signals background is probably very familiar. If you don't come from those backgrounds, these are basically the way that different frequencies of sinusoidal inputs are transformed through the system. The dynamics turn out to be surprisingly linear. The dynamics of the human, their transformations turn out to be surprisingly linear. And so the way a sinusoid gets transformed is it gets scaled, the magnitude changes, and it gets phase shifted by some amount. And so overlaid on this plot are the inverse of the dynamics, the machine dynamics the human is trying to control. In this case, it was a first-order velocity-based interface. And so the inverse model is shown in the dashed line. And you can see that the feed-forward transformation F actually does a pretty good job of approximating it. Gets the kind of general trends. It gets the right phase lead of about pi over 2 in the phase component. And then in the magnitude component, it gets the right trend. There's kind of this linear increase. Interestingly, it's sort of scaled down. There's sort of this systematic bias. So the human doesn't exactly invert. It does a good approximation, but there's some bias in it. And we'll return to that idea that the human isn't purely trying to maximize or minimize error. They might be trading off with some other priority. For instance, the amount of effort it takes to perform the task. So these are results with a first-order model. We can do the same thing with a second-order model. The main reason I'm showing this is the main reasons that I'm showing this are it's nice to know that these same general trends hold when I change the system dynamics. But then also, maybe more importantly, the model that gets learned here is just categorically different from the model in the first-order system. So people adapt well to the systems they're controlling, and therefore, if the systems they're controlling are different, then the human controllers end up very different. We've done a similar thing, as I alluded to at the beginning, with, do we have any questions? Yeah. Oh, okay, never mind. We've done the same thing with myoelectric muscle interfaces. This one was a very simple, I'll show a high density version later, but this one's very simple. There's just electrodes on biceps and triceps, 2 electrodes. And then it's just the difference in the activation of your biceps and triceps that acts as that one-dimensional cursor input. And so we wanted to compare these two, and the idea was, these probably have different dynamical properties. Is one strictly better than another? how do they compare? And so we can look at two metrics of performance. One is the actual tracking error, which is the task what we assign as the task is to minimize tracking error. Of course, the human might have other priorities as well, but this is at least what we have prescribed to them. And then we could look at another metric, which is how well have they learned to invert the model. So that's in the right column. And what we find that's kind of interesting is that when it comes to the tracking error and when it comes to the inversion error for the first order system, these two interfaces are pretty comparable. They're not seeing significant differences between them. But then when we look at the inversion error, so how well the human has learned to invert the system dynamics, we see a big difference for the second order system. And lower error is better, and so the muscle interface, they're able to better internalize those second order dynamics. I don't have a question that I get almost every time I give this talk so I'll just preempt it, is why? What's the mechanistic explanation for this difference? I don't have a good answer to that. But one plausible hypothesis is based on the observation that before my hand can move, my muscles had to have activated. And so there's going to be some difference in delay for a muscle modality is going to have less delay, I would expect, than a manual modality. And so it could be that difference in delay that's helping them to better implement those feed-forward signals. So this is wrapping up that first segment of the talk. What we've shown is that humans adapt to the dynamical systems they're interacting with. It's not a surprising or a controversial point, but it's all part of the story. It's all part of the journey we're going on right now together, building up these blocks one at a time. And in particular, what I want you to take away from it, as I was saying before, is that humans learn different models depending on the system they're interacting with. So that in the second part of the talk, I'm going to start dynamically varying or adapting the machine with some learning algorithm. And so then the human is going to respond by doing its own learning, and now all of a sudden we're in a complicated situation. So the key observation here, other than the key observation is that humans learn to approximately invert machine dynamics. So if you present with different machine dynamics, you get different human models. And so now I want to kind of flip the script and look at what happens when the machine is learning its own model or doing its own learning or adaptation. And so we return to this picture, and what I want to do now, h is already a function of m, but I want to make m a function of h. And I want m to be, as a function, to be changing in time or as h changes. And so fundamentally what happens, mathematically what happens, is we get a game, mathematical game. Distinct from when I referred earlier to my experiments as being video games that the users are playing. This is a mathematical game where I have two decision-making agents that have potentially differing or conflicting priorities. They're not perfectly sharing information with each other. They're not perfectly coordinating or colluding. And so we're in this kind of mess that we need to figure out what's going to happen. So one hypothesis, a hypothesis we base our approach on, is the idea that, well, both of them, the way they're making decisions is by minimizing some cost function, right? And there's a ton of this idea has recurred many times in the human, like motor control literature, BCI literature, HRI literature. It's kind of a fundamental touchstone for modeling what people do. It's a fiction. People have a lot of different priorities and a lot of different motivations for making the decisions they make. But, in certain circumstances, if we prepare the environment properly, if we're kind of restricted to, some favorable circumstances, they will approximately solve optimization problems. So we can leverage that in analyzing and trying to make predictions and shape outcomes in these kinds of systems. On the machine side, very common that machines adapt and learn by solving optimization problems. What's the loss? And then I would just run with it, right? Of course, there are other ways that I could program my robot, but minimizing a cost is extremely common. Another kind of principle we bring when we look at this problem is we don't assume that the agents can exactly globally solve this optimization problem. So we assume that they have some form of bounded rationality. And so rather than perfectly globally optimizing a problem, they might have to do some kind of local search method, something gradient-like. And so I might have my machine literally running gradient descent, And then I might hypothesize that the human is maybe doing something analogous, at least using local information, making small changes in their strategy, observing the consequences, and then trying to, descend a cost landscape roughly in that way. But that's an open hypothesis. I'll present some indirect evidence that humans are doing something like this, something that's consistent with this in a few slides. But that's kind of an open, question of what people actually do. So to study this, we created what I think of as the simplest possible human-machine interaction game. So we literally scalarized the problem. So the human has one-dimensional, kind of like in the first part of the talk, a one-dimensional decision variable it gets to choose. It's a continuous decision variable. We're not playing finite games. We're playing continuous games. And it's continuous in decision variable, and it's also continuous in time. They get to continually change this and update this over time. And then similarly, the machine has its own scalar variable. It gets to vary over time according to one or another of learning algorithms. And then we're looking at the interaction between the two. So we assume that they both have their own cost functions. In our experiments, we prescribe the cost function to the user. And we do that for the purpose of doing the basic science of what happens when we have these differing cost functions and these differing adaptation algorithms, and how do we change the outcome here. So for our initial experiments, we prescribe it, but then in the last experiment I'll talk about, we actually leave it up to the user, and then we're able to predict how they're going to change their strategy based on just some rough approximation or idea about what their cost function probably looks like, what some dominant terms in their cost function probably are. So when I have these two cost functions, there are a number of, let me start here. When I have a single cost function I'm trying to optimize, there's really only one prediction of an outcome, and that's minimizer, local minimizer, global minimizer. There's really only one candidate for the outcome of a good optimization algorithm, an optimization algorithm that's working correctly. When I have two cost functions and they're not exactly aligned or exactly opposed, in the case of like a zero-sum game, if they're in general sum, is a term that's used, then there's a lot of different candidate outcomes. It could be that we end up at either the human or the machine's global optimum. It could be that either the human or the machine just wins the game, right? Not super likely, not generally what we want as the outcome, but it's a possibility. But there are many other possibilities. So if I look at the best response functions, which say, let me fix one of the decision variables, the humans say, and then let me find the optimal response to that for the other agent, the machine say, and then look at that parametrically as a function of that first variable, I get these best response curves. If the costs are quadratic, then the best responses are lines. And so this is a cartoon, but it's actually kind of a faithful cartoon. It's accurate representation of what happens. Where those response curves intersect is called a Nash equilibrium. If people are familiar with game theory, they're often familiar with this equilibrium concept. One way to define it is by the intersection of best response curves, as I just did. Another way to define it is it's a point in this joint action space where neither agent has an incentive to deviate on their own. So you and I are playing the game, and we're at a putative Nash equilibrium, and if it keeps her action the same and I change my action, my cost increases, and I'm disinclined to make that change. And then symmetrically for as well. So that's another possible outcome. It's not inevitable. Some people think that the Nash have the mistaken impression that a Nash equilibrium is the inevitable and the only kind of ultimate outcome of a game, but that's not true. There are other possibilities that arise in different circumstances and arrangements. Another one is a Stackelberg equilibrium. We're going to specifically focus on a human-led, but these show up when there's an order of play. That's where this idea comes from. And so in particular with the human-led, the human is going to choose its action and the machine is going to quickly adapt. And so in that way, the human is leading and the machine is following what the human is showing them. And then a final equilibrium concept we're going to talk about is called a conjectural equilibrium. Formally, it's a consistent conjectural variations equilibrium, CCVE, but I'm not going to punish you with those 4 words in that horrible acronym. So I'm just going to call it conjectural for the purpose of this talk. And the way this arises is kind of very naturally from Stackelberg, right? So in Stackelberg, human is playing an action and machine is kind of best responding. that means that things are going to turn out, the Stackelberg equilibrium is almost certainly worse for the machine because the human gets to kind of control the show, right? They get to run the show. Suppose now that the machine decides, I'm not going to adapt so fast anymore so that I'm the follower. I'm going to slow down and maybe play a policy and kind of disrupt this leader-follower game that's happening here. If the machine is building a model of what the human is doing and then responding to that, that's where we can get into this conjectural world. It's where internal models are being formed by both the human and the machine, both players in the game. So then we instantiate this, and it's kind of similar in terms of humans sitting at a computer screen. What they're doing is they're using their mouse or touch screen to just move horizontally, a cursor horizontally, and then their vertical bar on the screen is getting larger or smaller, and they're told, keep this bar as small as possible. And so their manual input, their one-dimensional manual input, is influencing the height of that bar, but behind the scenes, invisible to them, a machine action, machine decision variable m, is also influencing the height of that bar. So this is the cost function we prescribe to the user. And we run these experiments on a crowdsourced platform called Prolific, so we can collect lots of data very quickly, very cheaply. People play this game, it takes 10 minutes for them to play it, and they get a couple bucks, basically. But it makes it very nice to scale up. In my group, we run a lot of human subjects experiments in person, and like n of 10 is reasonable for a paper, and it takes it takes a couple hours per subject, and so we're talking about with setup and breakdown and blah blah blah, it's a week of somebody's time. In contrast, to collect n of 20 or n of 100 on this platform takes you push play and you go to lunch and you come back and you have your data essentially. Just to throw that out there, it's kind of the scientific mechanical Turk basically. Okay, so I have results from 3 experiments to present. In the first experiment, the machine adapts using gradient descent. Kind of the most obvious algorithm, like let's just run with that. And there's a hyperparameter in this algorithm, which is the adaptation rate or the learning rate alpha. And so we varied that alpha from very slow to very fast, and then we looked at the outcomes. And what we find is that as learning rate increases, we systematically shift from Nash equilibrium at the slowest learning rate to Stackelberg equilibrium at the fastest learning rate. And intuitively, this makes sense if we think of Stackelberg as emerging from an order of play, because if the human is kind of, moving their mouse cursor at whatever rate they're moving it, human speed, if the machine is adapting very, very quickly, it's descending its gradient, the gradient of its cost landscape super fast, then it's going to essentially solve its best response function online and continuously in time while the human's moving around. So it's not surprising. These outcomes aren't surprising, but it was nice to see, and it's nice to see so clearly. If we look in the action space, we start at the Nash equilibrium, which are the bottom dashed lines, and we kind of continuously converge to the Stackelberg equilibrium, which are the top lines. In the second experiment, and an interesting takeaway here is these results are consistent with the human doing something like gradient descent on its own cost. I want to make it clear this is not direct evidence of that, so I'm overreaching a little bit in making this statement or conclusion. But it's at least human actions are consistent with using gradient descent. And we have very simple simulation models for what the human's algorithm could be that recapitulate these results. But basically, if they're doing approximate gradient descent, then this is what you would expect. So in experiment 2, we're targeting this conjectural equilibrium. And like I said, this arises from the following kind of thought experiment that I remember distinctly. I don't know if you remember this, Dorsa. We read these Bayesian games papers by Zamir right at the end of my time at Berkeley. And it always stuck with me, the following iteration, where I have these 2 agents, and the human, as we saw in the first part of the talk, builds a model of the machine that it interacts with, right? So it's kind of natural for the machine to build its own model of the human, which we also did in the first part of the talk. We estimated models of the human, feed-forward, feedback transformations. But then if they're playing a game, they're strategic decision-making agents, and they want to minimize their respective costs, potentially at the expense of their opponent or the other player, then it's in the human's best interest to build a model of the machine's model of the human, and then symmetrically, and so on, right? And you get this infinite regress. And there is this theory, this type theory, and different kinds of ideas that I'm citing here from economic game theory that try to actually computationally or actually analytically handle this infinite regress and then come up with models for the limiting process. We adopted a kind of different perspective where we directly model and measure the models that the users are building of each other, and then analyze as this regress is happening kind of in real time and rolling out over time. And so this is the idea of conjectural variations. It's been around for a long time. It's funny, I like to get the old citations for stuff in addition to the new citations, like the initial idea as well as like the good reference for the grad students nowadays. And what's kind of funny is that the reference for the Nash equilibrium concept, which is kind of the simplest, is the latest. And then the reference for the conjectural one, 1924, most complicated concept, is the earliest. It's kind of a funny little inversion here. So the way that we actually cache this out, I said before, or I observed before, that since costs are quadratic in our game, we prescribe quadratic costs, then the machine's best response to the human is a linear function, an affine function, but linear because of the coordinates we chose. Similarly, it's kind of natural to hypothesize that the human's response function is going to be linear. And so then what we do in the experiments is the machine kind of jostles around its policy parameters to estimate the parameters of this human model. And it jostles basically the offset in its policy. And then it takes that model and then it solves its optimization problem to decide how to play the game. And you could imagine the human maybe doing the symmetric thing, building an estimate of the machine's policy and then best responding to that policy. And so if we run that iteration in our game, like just computationally we run the iteration, then that converges to this conjectural equilibrium type, consistent conjectural variations equilibrium. And so we run that experiment and we find that's the result. We get exactly that result. We see that we started at Stackelberg equilibrium. Like I said, it's kind of natural. This is kind of a natural extension to Stackelberg, where initially the machine has no model of the human, but the human has a model of the machine's policy. And then the machine begins by building a model of the human, and then the human builds a model of the machine, and we iterate, basically. And where we're going to converge is a place where the policies that the individual agents are playing are, in fact, the policies that their opponents are estimating. That's the consistency in the definition of this equilibrium concept. And yeah, we see exactly that shift. Then, yeah, and I forget that I have these takeaways. And then, so the takeaway is that the human here, this is another instance where the human is learning, this is strong evidence the human is learning an internal model for the machine. If they weren't, if they were just playing a fixed policy, or if they were just continuing to just naively run gradient descent, like in the first experiment, we would not expect to observe this outcome. But this outcome arises when both agents are iteratively building and updating these models. Yeah?
So you talk about bounded rationality, and I was wondering if bounded rationality shows up anywhere, like in some of these experiments that you guys have had, and what would be the form of bounded rationality? Like, the reason I'm thinking about this is we kind of like have this infinite regress, and remember like back like a couple years back when we were looking at driving, you could argue when you're driving right next to another car, you could have this infinite regress, but in practice that doesn't happen because you have limited time. And because you have limited time, like there are these user studies that say, well, you at most do 2 levels of theory of mind. You don't actually like do the infinite regress because you have so little time to decide what to do and like and machine here is like the other car, and like you're like the driver of like your own car. So you start seeing like some of these bounded rationalities kicking in terms of like the interactions, and I was wondering if you have various forms of bounded memory, bounded time, and if they show up in some of the experiments you guys were looking at.
Yeah, that's a great question. I guess it kind of, to me, it sort of shows up differently in, I'm gonna present one more experiment from this paradigm. And it sort of shows up differently in each of them where we have a sort of naive model of what the human's going to, or like, maybe not naive model. We have a mathematical model for what the human's going to do. You know, we say machine does X, we predict human does y. And if machine does x and human does y, then we should arrive at this equilibrium outcome. And if the human wasn't doing y, we should not arrive at that equilibrium outcome. And so in each of these cases, we are observing convergence to the predicted equilibrium. And so to me, that's a form of, this is the limitation on the human's rationality. They are playing the game at this level. They are not going another layer deep, more deeply.
To kind of like set that and categorize like what are the different equilibria that they're reaching under humans.
Yeah, exactly. Like the equilibrium concept is the thing that characterizes how deeply the human is reasoning in that particular game, or in their response to that machine algorithm.
And maybe one follow-up to that. So, like when we think about like bounded rationality, it could capture like how many layers deep you're going, but it could capture other things too. Like another example that comes to mind is like there's this game of lunar lander, right? And it's motor control, like kind of like a game. And I remember there was a paper from like Anka's group a couple of years back where they were saying, well, humans are not bounded rational when it comes to playing this game. The reason they're bad at playing, the reason we are bad at like playing a game of lunar lander is we think we are doing Cartesian control, but in practice, like you're controlling like the acceleration and the motors. But you think, you know, like we as humans, we think in Cartesian control, and that is the reason like the model is off. So it feels like there are these different forms of boundedness, or like how humans make decisions. And so in reality, if you have seen any forms of various forms of bounded rationality, or mostly like you're looking at like how many layers of thinking you're going down the tree.
Yeah, that's really interesting. I guess one observation is, from the first part of the talk, is there are bounds that show up in sort of the sensor-motor transforms people learn and implement. Whether those are bounds on rationality or just bounds on neurophysiology or something, I'm not sure how to tease those apart. But yeah, it's I hadn't thought of it that way before. But I think like one way to think about my talk is it's kind of a sequence of vignettes about the limitations on human abilities while interacting with machines, whether it's kind of at the sensor motor skill level or it's kind of more cognitive. Cool. Any other questions? Okay, I'm going to go into experiment 3. And here we were interested in trying to steer the system outcome to where the machine wants it to go, to the machine's global minimizer. And so here the machine does kind of so I'd say the like straight up gradient descent on actions, probably the simplest, most obvious algorithm. Policy gradient, probably the next simplest, most obvious algorithm. And so here, machine implements a policy. It varies the slope, a policy as a line, an affine subspace. And then it manipulates the slope of that policy, observes the outcomes, through how the human responds, like through that whole closed loop, and then descends that noisy cost landscape. And we see that just running this very simple-minded algorithm converges to the machine's global minimum. In the game theory literature, doing this kind of thing is referred to as designing an incentive for the human to change how they behave. And in that case, the point that you converge to is called a reverse Stackelberg equilibrium, or RSE. I just mention that as an aside to anybody that does this kind of work and is interested in those results. But the point being that we can literally coerce the outcome to anything we want just by doing an incredibly simple algorithm. And so here is another demonstration of the limitations on rationality for the human, because if the human realized this is what was happening, because keep in mind that the machine's minimum is far from the human's minimum. So in terms of the prescribed cost, this is a much worse outcome for the human. If the human could get wise to what the machine was doing, then they could play their own policy and then start iterating at the level of their own policy in the game. But here it appears that they just do the kind of naive gradient descent thing they were doing in the first experiment. And so then we get this outcome. And in essence, the machine is outsmarting the human in this game. It's manipulating the interaction to achieve whatever outcome it wants, which I think is a if not wholly surprising, it could be potentially a sobering observation that, in the learning algorithms we interact with machines in our physical environment, could actually strongly determine or constrain our behavior, actually influence our behavior in a really strong way, even with very simple algorithms. So returning to this kind of constellation we had originally, we're able to achieve a wide variety of game theory equilibria, and importantly, the way we select them is by the machine choosing a learning algorithm. And it's the choice of machine learning algorithm that determines the outcome in this interaction. Human is continually adapting and learning on its own, and they're intelligent and can reason in various ways, but the machine is essentially able to steer the outcome to wherever we want it to go. So then the final experiment I want to talk about is taking these ideas away from these kind of like scalar little inputs for the previous paradigms that I talked about, and into a higher dimensional, non-invasive, we call it a brain-machine interface. My collaborator is a legitimate, neuroscience brain-computer interface researcher, so she gives me permission to call it a brain-machine interface. It's going to be a surface myography that we're measuring, but it's nervous system, right? It's electrical signals. And so we have this high density electrode array, 64 channels, that we put over a patch on the forearm. Those signals get integrated, and then they get multiplied by a matrix that kind of decodes and down selects them. So we start with 64 EMG electrodes, and then we end up with 2 dimensions of cursor velocity. And then we just integrate that cursor velocity to display a target on a screen, and then we have this reference. So it's the same kind of paradigm from the first part of the talk, not the bar on the screen, but now the squiggle on the screen that we're trying to track. But now the input is provided by this electromyographic interface. Yeah?
Sensors far forward enough to detect the tendons that control the fingers?
This is a super fancy EMG, so it definitely can. We're only using it for we're using it for 2 dimensions of input, so it's just very gross kind of wrist movements. But this is a Quattrocento high density device. Oh, thanks.
So here we are doing agents function of M, but could we do the other way around with the same setup where you're able to make humans learn from the machine?
Are you meaning in just the previous part of the talk?
No.
So in this one, okay.
So here is the sensor. We're using a sensor to you give the instructions to the machine. Could you do the other way around with the M to H interface?
Yeah, so in terms of the sensory display, yeah, absolutely.
Let's say someone is visually impaired and you're able to let them know on their skin whether they an offset.
Yeah, absolutely. Yeah, my sort of high-level vision in my group is you have the user, in terms of a block diagram, is you have the user, you have the machine you're trying to control, the robot or whatever it is, and then in the middle you have the interface, and the interface is processing both the motor pathway, the motor commands from the person, and the sensory feedback to the person. But we haven't done it yet. Yeah, but I'm very interested in, what does this look like for haptics? With a kind of sci-fi vision that Amy Orsborn, who's pictured there, and I had for a kind of high-risk grant that NSF funded was for invasive neural interfaces. You can put electrode arrays in sensory cortex, and you can actually render new sensory data. And so you could make an artificial, one dimension of continuous feedback so that they could play the tracking game or something. So in our block diagram, what we're doing here is we're deciding that our machine is going to have a cost function, and it's going to be a combination of the tracking error and the decoder effort. So as a gain matrix, how big is this decoder matrix? And then kind of symmetrically, we're going to hypothesize that the brain has the same cost. This is a common hypothesis that's been proposed by a bunch of other people over the last 20 or so years. And importantly for this part of the talk, we don't need to know exactly quantitatively what this cost function is. We just work from the general structure of the cost function and then make predictions and shape outcomes. And so the structure of these costs are that they have this linear convex combination of, or this weighted combination of error and effort. And then we have this hyperparameter multiplying the effort term. And why do we even have these effort terms? If they aren't there, then the trivial solution to the game is that we should crank up the gains as high as possible to attenuate error as fast as possible. And it's just not realistic. It's not plausible that the person can implement that, and you'd just be amplifying noise if you tried to implement the decoder to do that. And so it's kind of a regularization that trades off between these two things. It's very common in control theory. If I'm solving an optimal control problem for a linear system, I have like an LQR problem. I have a Q term and an R term. I have a state penalty and a penalty on the input. Same idea. And we can use this analytically to make predictions about the outcomes in this game. And the prediction is very intuitive that the decoder and brain together are going to learn to approximately invert one another. So this goes back all the way to the first part of the talk, where what people are learning when they're interacting with machines is how to model and then invert their forward dynamics. And so these turn out to be the predicted equilibrium outcomes. And they're scaled by this penalty parameter. Basically, the introduction of the penalty parameter means you're not going to get zero tracking error. You're going to get some amount of tracking error. And the amount of error is proportional to that parameter. And so the predictions we make are that if we look at this in this exploded kind of feed-forward, feedback diagram, we predict that the encoder is going to be matched to the decoder. So the decoder is just this first-order velocity interface. And so then we think that the controller is going to have zeroth-order terms and first-order terms. So in terms of control theorist feedback, proportional terms that are proportional to error and terms that are proportional to the time derivative of error, P and D terms. And then we make this prediction about the approximate inversion, and then also that it's a stable closed-loop system. And so then what we're able to do experimentally is measure these F's and these B's and then test these various predictions. So basically these predictions bear out. If I look at the terms in the kind of zeroth order term, they're approximately zero. If I look at the terms in the first order term, they're almost an identity matrix. This gap along these diagonal terms kind of goes all the way back to the first part of the talk where I had the Bode plots. And I showed what M inverse would look like in magnitude, and then what the feed-forward controller actually looks like. It's an attenuated version of the actually exactly inverting controller. And then we get stability of the closed-loop system. We already knew the closed-loop system was stable because the cursor didn't fly off the screen. But this is more a validation that our estimation methods make sense and give kind of consistent predictions. So we get consistency with our control theory predictions for the system. And then we're going to vary that penalty parameter and see how that shifts things. And what we observe is that by cranking up that penalty parameter so we don't get to change the human's cost function. That one might have penalties, it might not. We don't have control over it. But we do have control over the decoder, the machine's penalty parameter. And so if we crank that up, then for high lambda, the decoder effort term gets smaller. Very intuitive outcome, not surprising, but it was good to see it bear out in practice. And then the opposite happens for the encoder. The encoder has to crank up its gain to compensate. And so then at high lambda, we get a larger encoder effort. So this is consistent with our game theory predictions. And so the takeaway here is that we were able to not only predict the outcomes we were going to get by going in and tweaking the machine learning algorithm, the machine's cost function, but we're also able to shape it in the sense of manipulating user effort while they're using this system. So you could imagine in like a rehabilitation context, you might want to be, the clinician might want to be able to systematically change the amount of user muscle activity or effort they're exerting in a particular treatment. And so this gives a kind of principled, systematic way to achieve that kind of manipulation. So that concludes the second part. The big takeaway is that these machine learning algorithms can shape outcomes. We can, in one class of experiments, select from a whole constellation of game theory equilibria, and then in another experiment, we're able to nudge the user in a desired direction. And so I just want to advocate for this idea of bringing game theory into these human-machine interactions. It's something that I've been really excited about for years, and that I think needs more recognition, has more potential to grow. So with that, I'd love to thank you for your time, and love to take any questions.
So you talked about like game theory ideas, and I was wondering, and you talked about it in the context of motor control, but how do you think like things would change if you go outside of motor control and talk about other types of human-robot interactions? Like in the morning you were talking about these dyadic interactions, where there's a robot arm and there's a human, and they're trying to make a sandwich here. So like, do you think similar type of ideas apply there, or like have you been looking at mostly motor control tasks, or how should you think about the bigger scope?
Yeah, it's a great question. I'd say my particular interest and focus is on situations where the machine is really attached to or tightly integrated with the person, and either restoring or like adding or augmenting, like you said, motor control in one variety or another. So I can foresee really obvious generalization of these kinds of results into like invasive neural interfaces, because we already did non-invasive, or wearables, exoskeletons, things like that. For the co-robots, if I had a good idea, I would be doing it. I think it's my pithy answer. So yeah, I'm not sure what the right way to do it is. I guess there's kind of maybe I shouldn't end by being controversial, but there's sort of an issue, which is, should robots and people be in the same spaces doing stuff? It's kind of this general question, but yeah.
Yeah, so it's more of a functional question. So we had like tools to, let's say, for humans to learn about the machines, but we are doing it both ways. So even machines are like learning about humans in the full model. But now that we have the semantic models, so it might be like a different unique paradigm where we can like enable machines to learn more about the human interaction. So what do you think about that future?
I might need you to restate or rephrase your question.
Okay, so just like humans are learning about machines, machines are learning about humans in this model, but machines did not have, let's say, LLMs before.
Okay.
And now we have LLMs, so maybe machines have better tools to learn about human behavior. So in that way, how do you see the future?
I see. I think I might have really dissatisfying answers for two questions in a row. I would love to see and test whether any of these ideas show up in that complex of an interaction. I think there are possibly hints that it might. My collaborator, Lillian Ratliff, who's the game theory expert, has taken some of these basic ideas and then shown how the different outcomes can show up when you have two like large-scale learning algorithms interacting with one another. And so that's kind of more broadly, that's one direction this kind of work could go in, is not even human-machine anymore, but just machine-machine, two AI algorithms. But yeah, it would be beautiful to see a Nash equilibrium between an LLM and a human, I think we need to, it's kind of similar with the human robot space. Like, what is the problem? What is the cost function that we think the human might be minimizing and that we would want to design a machine to be minimizing? So what is the task? What is the problem? That's my very dissatisfying. I'm dissatisfied with my answer to your question, but that's what I've got. Yeah.
Earlier you mentioned that you used the gradient descent method for finding the optimization, and I was wondering if you use using a direct method like the Hawks-Heaps method. I was wondering if using a direct algorithm that wouldn't require you finding the gradient, how would that impact the results?
Okay, that's really interesting. I'm not familiar with the particular scheme you're talking about. Can you describe, like, is it a zeroth order method?
Well, it's a second order method that requires no gradient.
A second order method that requires no gradient?
Yeah. Wow. It doesn't require you just finding the gradient to find the optimizer.
But so is it estimating the gradient from function evaluations, or?
Well, I'm trying to recollect how that works. So basically, it kind of goes over the searching different minimizers and just like optimizing as it goes along, but it requires no gradient. So I was wondering if using a direct method would impact the whole result.
That's really interesting. I think so again, not knowing any details about that particular method, I think my general answer would be that, based on what we've observed, different algorithms give rise to different outcomes. Right. And so you might imagine that you end up at a completely different equilibrium concept. Yeah. Yeah.
I'm curious to hear what are your thoughts on maybe using some of the conclusions from your work and applying that to, for example, a case like sports. Because in my head, I'm thinking about how, for example, in a tennis match, two players are like really trying, like ultimately as a player, you're not just reacting to what's happening in front of you, but also trying to figure out how your opponent plays. Mm-hmm. And in a way, I feel like that's very similar to the human learning about the machine and the machine learning about the human. And I wonder if this kind of framework could be applied in those sort of circumstances where like a human's ability to do a certain task could improve, could be in sports, could be in something else as well, like in a particular game.
Yeah, no, that's super interesting. Maybe tennis might be hard because we don't have robots that are that athletic, but maybe table tennis, I just saw demo of that. I really think that these ideas, I really think that people are, as they're playing games like that, competitive games, building models in real time and updating them in real time. And then, any weakness in the opponent's strategy is being, instantly exploited, basically. So it would be super cool to see, to endow machines with that same level. I have a 7-year-old, and so playing some games with her, either board games or sports kind of games, it's interesting to kind of probe her level of reason and the bounds on her rationality and things like that. Yeah, I think it'd be fascinating. Great. Thanks everybody for your time. Have a great weekend.